4.2 custom iterators. This is a fairly straightforward piece of content today. It is really useful and important for assignment 2. It's a part of assignment 2. Part of assignment 2 is to make your own iterator. So back in week 2, we talked about STL containers, STL iterators. And assignment 2, in a nutshell, which we're talking about next, is creating your own STL container and creating your iterator for it. Because something that wasn't obvious to you maybe back in week 2 is that the iterator for the iterators that join containers and algorithms actually exist within the container. So the container defines itself and it defines its iterator, its kind of abstract I/O point, and then algorithms work with that iterator. So I just might make this bigger because I think people had problems with the lecture. Oh, is that this one it didn't cut off? No, this one's fine.
Can we get it on both slides?
Yeah, I will. I usually do it after 5 minutes once people get the Slido. Some people take a moment to want to post a question. So when we define our own types, our own STL containers, we want them to be iterable, makes sense, so we need to deal with iterators. Now, the start of this is going to be a little bit of light revision. I don't want to spend too much time on this because you know what? We talked about iterators 16 days ago. It wasn't that long ago. But the two things to point out are that iterators are the glue between containers and algorithms. The designs of algorithms don't care about the details of the data structure because of the iterator. And it allows us to write code kind of like this, with .begins and .cbegins and stuff like that. And we also need to account for iterator invalidation. We also talked about this a bit more than normal back in week 2. And here's just a few code examples to help you out or to help unpack it a bit more. We talked a lot about there are functions like pushback or erase that will invalidate the iterators they have, and you can generally get around that by returning the iterator. This is an example here. We coded up a really similar example to this one back in week 2. So we'll get today's lecture done faster because we don't spend 15 minutes unpacking that. But just remember, with iterators, they might be invalidated. If you're not sure whether an iterator is invalidated, go to the CPP reference docs. It tells you there whether something's invalidated or not. Mostly it's around mutations. If you're kind of altering the structure, then that's probably the main thing that does it, particularly for vectors, because vectors have to do some shifting and stuff. All right, so iterated traits. When you define your own iterator, right, there's a certain thing that every single iterator has to have specified for it in terms of types, and we call these iterator traits. These basically appear as like a struct with various types. You'll see a code example soon. We give it a category. This is the category based on input iterator, output iterator, forward bidirectional random access. If you remember that back from 2.2 lecture, we talked about how like a vector iterator is random access because you can, do like iterator plus equals 6 and like jump 6 spots. Whereas there are other iterators like the doubly linked list or the forward list iterator where you can't just jump 6 spots, but you can move in either directions, and those ones are bidirectional iterators. So a lot of the containers that you've probably dealt with that have iterators are probably bidirectional or random access. And then we also have to specify for this iterator what's the value type, reference type, pointer type, difference type. I think with a lot of this stuff, and we'll see the code examples, there's not really a ton to unpack here because it's quite boilerplatey. And again, a lot of assignment 2 is boilerplatey. If we have a look at an example class like this, now maybe I'll pull this up in code so we can see it a bit clearer. This is an example of what an iterator, a custom iterator, an iterator that you make might look like. You can see here that we have kind of used t as a placeholder for an actual type, because the type could be int or something else. Like if this was a vector of strings, then the t would be like, it would be a t. But if this was, say, a vector of ints, then all the t's would be int, for instance, because you're iterating over ints in a vector. But these are the iterator traits that I've mentioned. So when you define your own iterator in C++, you need to put this section up the top. You're basically here, like using is a way of type aliasing, because we've kind of seen that with the whole namespace element. So we're just kind of type aliasing stuff here, kind of type defing where we say within the scope of this iterator class, this name, this name, this name, this name, and this name are all referring to these particular types. The good thing about iterator traits is that there's not actually a lot to it, because like you just copy and paste this and you change t with whatever you're doing, you know? So this isn't some like kind of really technical sneaky thing where it's like, oh, sometimes you got to account for this. It's honestly mostly copy and paste. The only real things that I see that are different are you typically have to change this one from like, you know, forward iterator tag, and then you think, oh, I don't know what the random access one is. So you say like, you know, custom iterator.
Is the T here actually mean anything? Is it just a template?
Sorry?
T. Is it actually, can you actually put there? Or?
Yeah, it's just a template. So in this case, it wouldn't actually compile. It would just not compile at all. It would just totally fail, because it doesn't mean anything. Later on in the course, in like week 7 and stuff, we get into like dynamic polymorphism and templated classes where we'll do something like that. But for now, you would actually replace it with a specific type you want, such as int. But yeah, like you can kind of Google this stuff. It'd be on the CPP reference. The differences, I don't know what I clicked on there. I think I just clicked on the first one. Writing a mod, you know. And my point here is not to say, oh, like, wow, Hayden doesn't know where things are. My point is that you, like me, like everyone else, will end up at some point thinking about something like this maybe in 2 years, and you're going to forget what the hell a particular tag is, and then you're going to Google it, and then you're going to be like, oh, that's right, random access tag. What's cool about the CPP reference website here too is that it actually kind of shows you the relationship between them. Like it shows you have an input and an output iterator tag, which are quite simple. And then you have a forward iterator, which this is, we don't get into this until like week 8. This inherits, this colon syntax is inherits. It inherits the input iterator, and the bidirectional one inherits the forward iterator, and the random access one inherits the bidirectional iterator. And then there's another one, which, honest to God, I've never seen before until I loaded this page up with you right now, called contiguous iterator. That sounds really interesting. Sounds like something that, you know, it's like random access stuff generally are contiguous things like arrays and vectors. So I'm imagining that's some kind of extra thing on top of random access where you get some benefits. Wonder if we can learn about that here at all. Probably not on this page. Sounds like something interesting to read about though. Sorry, I'm searching the wrong one. What do we got? Oh God, I can't stop clicking buttons. Contiguous iterator. Ooh. A guarantee that the denoted elements are stored contiguously in memory. That's quite interesting, I guess. Never really thought about that. I'm not going to pretend that I'm smart enough to comment on it, but I do imagine that it's an interesting idea, because I would have thought an idea like that kind of breaks abstraction and the whole point of an iterator, because the whole point of an iterator is to kind of abstract away the memory, but I'm sure there's some interesting use cases for it. But
is it saying there, but random access implies that it doesn't have to be one after the other? I thought contiguous meant that it has to be one after the other.
Random access simply means that you can jump without iterating. So like the way, like think about a vector with 100 items in it, right? And if I get the beginning of that vector, I can ask the vector to increase 20 spots, and it is able to do that in constant time. Whereas if I get like a list, it will do that if I plus equal 20 on it, but it will only do that in n time by stepping up one at a time.
So that means that the memory is one after the other.
The memory being contiguous is often what allows the container to do that efficiently, but it wouldn't be a requirement that it's contiguous necessarily. Like they could arrange, like it just needs to be somewhat deterministic. Like it just means the container, however things are stored, it is able to figure out how it can jump quite quickly from one spot to another.
And so that one's saying it'll always be contiguous.
Yeah, that one's saying like when you get back a particular element from the iterator, you can assume that if you jump in real terms, actual memory blocks up, that you'll get the element you expect. Yeah, but I can't think of a use case. Like, I mean, again, I'm not an expert in this field, so I'm like, okay, well, that seems interesting. I'm sure someone was like, this is really necessary for some particular use case I'm not familiar with.
What do you say about input and output iterators?
What did I say about them? Oh. Oh, what does it mean? They're typically the iterators that are used for things like, trying to go back now, I can't. For things like input streams and output streams. I don't really use them much. There's a couple of examples you can find online. But again, day to day for me, it's like everything's like forward bidirectional and random access, because you're mostly doing it with containers is the thing. Now, when you make a container, because here's the thing about iterators, when you make an iterator, what was that slide? Requirements. This is typically how it actually works. So you'll have a container class, like a vector, and that vector will inside it have an iterator. So to make this more concrete for you, what I mean is that you would typically take this, and this is kind of like how it might look something like this, right? This wouldn't compile again because I'm just using some random words, but you have a container like a vector, like an array or something. So imagine this is vector, and you can imagine this is like namespace std or something here, just to like really make it quite clear. So you got your namespace std, you've got your class vector, inside of that's an iterator. It has all the iterator traits which are necessary when defining a custom iterator. And then we have some extra functions which we didn't really unpack before, but these are the things that allow you to actually work with an iterator, right? Typically like a plus plus, minus minus, access the underlying element, equals, not equals, because like in the case of equals and not equals, you need to be able to have two iterators and compare if they're the same. But then when defining an iterator, you don't just need the iterator class definition that is contained within the container, you're also required to basically produce these things as well in the container. Because if you have an iterator, someone needs to be able to get the begin and the end of that. So if you have a container, someone needs to be able to access the iterator at the begin and the end of that container. And you also need to be able to have someone access the begin and the end and the C begin and the C end here. Now, there's a few things missing from this. So a little bit of assignment 2 is to figure out what's missing and kind of what pieces of code are there. For instance, like this code wouldn't work without me also defining a const iterator type, because that's what that's referencing. Which again, it's kind of what I said. It's like the nature of assignment 2 is trying to understand C++, right? Assignment 1 had very little to do with C++ because it was like week 1. And we were like, why would we like make you think too deeply about a language that you've just seen? So let's get you comfortable with the basics by making you solve a problem. You've solved a problem, now it's like let's play around with the language. But this is in spirit the gist of how an iterator is defined within a container. And naturally there's going to be a lot more defined in the container, but for the sake of a custom iterator, this is what's here. And if you were creating your own std vector that didn't have an iterator in it, it would look like this, plus all the other stuff, right? So all the code up on screen is the stuff that you need to add to make an iterator work, both in the container and the iterator itself.
Is this just like self?
Is this like what?
Keyword this here? Is it just like
Yes, it's like self in Python. Yeah, exactly. Yep.
What are the benefits of putting the class?
Yes, I don't think, I think it would compile for sure. I haven't been asked that, but I imagine that the reason this would be common practice is because just by the principle of no one should ever have to access the class scope besides the container. So why give it more scope, basically? But yeah, it would work outside of it. It would just be like, someone at work would just put in the what's it called? Code review. They'd be like, oh, that's probably not a good spot for it. That's all that would happen.
It already inherits random access, so that's like
It doesn't, yeah, so I mean, just to be clear, it's like the random access iterator tag here doesn't really have like, it doesn't give it like powers, if that makes sense. It's purely like it's like a note for the compiler. And this is actually how things work, because you know how like we talked earlier about like there's some algorithms out there like say, a quicksort's a good example. Like a standard quicksort needs to be able to randomly access things. If you think about quicksorts you learn at uni. So if you tried to run, a standard quicksort on something that is only forward iterating, a quicksort can't sort something that's only forward iterating, right? So what these tags are for is like, and we can maybe look one up. I can't remember what standard sort, where the info is off the top of my head, but I wonder if I can look up random. Yeah, random iterator. It's right at the top. So I couldn't go much deeper than this, but it's like the way that this particular algorithm's defined uses a random iterator type. So what the compiler is able to do is it's able to look at the container you're trying to, the iterator that's trying to apply this on, and the algorithm, and basically see if they, have some type.
It's like a check.
Yeah, exactly. And that's where the inheritance comes in, which again, we don't do anything with inheritance yet, because if you have something that's like random iterator, inherits the bidirectional one, because like if you had an algorithm that wanted to work on bidirectional, but your container was random, because random inherits bidirectional, they would also work, so it just uses those fairly straightforward OO ideas to get things together. Emojis. So this one here, I believe the code example we had, this one was for like a forward iterator. So this is what you would need for a forward iterator. If you're ever defining a forward iterator, I know I wrote random access here, forward iterator tag, that's what that should be. If you are defining a forward iterator, that's kind of the stuff you need. If you're defining a bidirectional iterator, you will also need to add this as well. You'll need to add the R begins and the R ends, and the const R begins and the const R ends, and the const CR begins and the const CR ends, right? Like you'll need to add those things as well. And it's not really written in the slides strictly here, but you will also, well, I think it's written here. You'll also need to add the operator minus minus. So it's not probably well described, but if you imagine that this is like your stock standard iterator, and I was to just copy it across here like that, you would also need to come in and be like, all right, well now I need my minus minus and stuff like that. And your it's pre-decrement, I think. I've honestly probably never thought about it before.
Is that the reference there? Just why do you kind of do it twice? You go to reference.
Were you here on Monday?
No, I read on it in the slides.
It was covered on Monday, but the quick gist is that pre-increment returns the actual item. So it's a reference to the actual element in the container, but post-increment, which is what this is, returns a copy of what was, like it returns a copy, then it increments the actual thing, so it returns something that's not going to exist forever, so therefore it has to actually copy it out of the function. Yeah, I think a little bit of that was on Monday. It's a good question. And then we have a few others in these slides. These slides are meant to kind of give you some useful stub code. Like what's this one here? Reverse. Yeah. So for me personally, this is not my favorite kind of stuff about C++. Because so there's people out there who work with C++ a lot, right? Like imagine your Optiva people, and they know every little thing about the language, and they get really excited about this stuff. There's all these little secret passages and ideas in C++, and this is an example of one of them, which is really cool, but I just wouldn't have ever known this existed if someone didn't kind of bring it to my attention excitedly one day 3 years ago, is that there's actually a type in C, well, not really, I don't even know if it's a type, but there's a, I guess a function, let's just look at the code together, here, where what you can actually do is, because if I take a step back and I make some bloody sense, here, if we have a look at our R begins and our R ends, you'll notice I haven't actually implemented them here. You know, these are just like the ones that are like, they're all just declared. They're not defined. And the ones that are defined in terms of the ones that are not defined. Right, so we haven't actually done the work yet. And the point of the next slide is to say, well, the cool thing about C++ is that rather than have to go and define all of these things again, you know, what we can do is we can actually take advantage of a particular class in C++, where what you do is if you pass it into reverse iterator, it will actually flip it around for you. So in this case, if I was ever defining R begin and R end, and just for clarity, again, this is your bidirectional file here. So we've got imagine we've got our normal iterators first, and then we've got our reverse iterators. So this would be a bidirectional iterator now, because we need to be able to go forwards and backwards. So we need to go forwards and forwards const, and then we need to go backwards and backwards const, is that you could actually come along and say, well, hey, to save myself defining even more stuff, what I'm going to do is do this instead, where I simply, for my R begin, I simply take my end and I call reverse iterator on it. And for begin, I call reverse iterator on it. Now, for people who are just trying to get started with C++, like many of you, and for people who don't work with this super commonly, like myself, in some ways this can feel a little bit more intimidating because it doesn't make a lot of obvious sense what the hell it's doing, right? It seems like this little bit of abstract magic, and you're like, I have no idea how that works. And you're at a stage where you're trying to concretely understand what's going on. When we talk about C++ being a powerful language with lightweight abstractions, these are the kinds of things that people typically mean, and what make it a lot closer to languages like Java and Python in many ways than C, is because if you are defining stuff, you can actually do a lot with just more and more abstractions and random libraries and things out there that will mean that you only have to define stuff at one point, like up here. In this case, we can get ourselves begin and end, const begin, const end. We can do most of those things with just defining maybe like these 4 functions, you know, and everything else is derived from those initial 4 that we define, because we've got our const reverse in here. So what's actually happening is that this here, this gets a little bit into metaprogramming, but this is the actual C++ element that does the kind of reversing. We're simply capturing it here and then using it here as well. So we don't need to do this if we don't want to. We could just have that. That's the same code there. We're taking a particular class, I believe, called reverse iterator, which is templated on the iterator, namespaced std, and then we're reversing that there. But that's how you would go and do a reverse iterator. Again, a little bit weird, but the good part is that a lot of this stuff is just copy and paste, frankly. So it's not a very inspiring lecture, I will admit. Is it like a hidden function that happens somewhere to reverse it? Well, if we actually have a look at it, standard reverse iterator, it is a templated class. So formally, it's a class. So if we reason with it for a second, this is a class in the std namespace, and it's templated on iterator. So what that means is in this case here, this is a function that returns a type reverse iterator of our underlying iterator. And this here would be a constructor because we're putting the type and then the braces next to it with our iterator. So we can scroll down in the docs and should be able to find it. The constructor. You know, we can see here that this reverse iterator takes in an iterator type. This iterator type would be defined to be that generic one. And this iterator adapter, like, it gets pretty deep. Again,
just create another class, which is the reverse of that one.
Yes. You're creating an object of that class type and returning it. I mean, because this is a type. Because a class is a type, right? This is the iterator you defined. Yeah. Look, I'm getting a few blank stares. I think that a lot of things like this only really make sense when you play around with it, but naturally this stuff isn't easy to play around with because the code's quite boilerplate. So what I'd say is if you're like, okay, I could never in a million years just sit down and write out that myself without an extensive amount of Googling and copying and pasting, but I kind of get what it's getting at, then that's a good spot to be in right now, you know? So if you're at that spot, then like, great. Because we're just trying to show you that there's our different kinds of iterators, just to give you a sense of it. Because you'll have to implement an iterator for assignment 2, and it's going to be a lot of just figuring out the exact right code and looking at other examples until you can get something compiling. But yeah, it's worth just trying to understand that. So random access iterators, just like the other iterators, have a few extra things in them. Namely, you need to be able to plus equals the iterator. You need to be able to subscript access the iterator. You need to be able to, like, you know, this is our friend operator overload. So we're overloading the operator for plus for the iterator so that when someone comes across and says, yep, here's my iterator, I want to increase it by some number, that it actually does move that iterator along in that direction. And then we have the same for minus as well. Two operator pluses, 2 operator minuses. And then we also need a bunch of less thans or greater thans here as well for the random access one, right? So the less than or greater thans, they become relevant just because with random access there's a notion of like being able to move up and down certain amounts, less than or greater than. Surprised that's not relevant for bidirectional, but let's just stick with this for now. But what you'll notice with a lot of this too is that the actual points of explicit definition here are really small. And what I mean by that's like with all this, we're still once again just defining a couple of examples, then defining other things in terms of the negation of it. What you'll also notice is that there's 2 pluses and 2 minuses. And the first one is like allowing you to basically say, if you had a vector, you could say, sorry for writing JavaScript, you could say something like, you know, v begin plus 5, like that. But you could also say v begin plus, you know, or like, what would you say? You could say, yeah, iterator that plus equals 5, and then you could say auto iterator 2 equals v dot begin plus iterator. Right, so on this line you've done iterator plus number, and on this line you've done iterator plus iterator. And both of those things are able to like exist, right? That's just like how it's defined. And that's actually where that difference type comes in, because if you remember way back, we had this this difference type here. And this difference type, I don't really remember why in the slides here it's an int, but typically it's kind of the same type you're actually dealing with, because it's just how many steps you jump. All that really is the abstraction of like when someone increases your iterator by 1, how far are you going? So I generally imagine that that's t, but a lot of the examples do seem, when would the difference type not be int? Well, I mean, it should just be, I'm trying to think, because oh yeah, it's a count. Yeah, that's why. Sorry, I was thinking the wrong way. It's like a count. So that's why it's kind of hard-coded as an int, because it's like we're moving 1, 2, 3, 4 spots. You don't move standard string Hayden spots forward. You move like 1, 2, 3, 4, 5 spots. Yeah. I mean, I don't know if you can. I mean, maybe you can. You shouldn't. I know that for sure, because like if it's, you said for, wait, did you say for bidirectional? Oh, non-random access. Yeah, like, because if it's non-random access, no one should be able to jump more than 1 spot, right? Yeah, I do believe that some are defined that way, right? So like, I think the example that we looked at was standard list, right? Because standard list had, no, it was, what's the algorithm where you like move and is like step or something? Someone remember? It's like the algorithm, you like give it an iterator, then you tell it how many steps you want it to do. Walk? Well, it was like, yeah, thank you. I think it was next. Yeah, so I mean, this all starts to make more sense for those who might have struggled with it. And I think these are always really interesting. And this is actually why these STL algorithms are so good. I've said this in week 2, so I'm sorry if you remembered it really vividly. But standard next takes an iterator and then it increases it, funny enough, by a difference type, right? All the pieces of the puzzle start to come together. So I give standard next an iterator of type input iterator. So that's the specific type for that container's iterator. And then I also have to give it the difference type of that iterator as well, which is probably going to be an int in this case. And what it does is it takes that iterator and it moves it a certain number of spots forward, and that only works with input iterators, forward iterators, bidirectional iterators, and random access iterators, right? Because moving forward is quite a universal idea with an iterator. An iterator that can't step forward is kind of a silly iterator, right, generally. However, what's interesting and why the abstraction's cool is because the complexity says it's basically linear for everything that isn't a random access iterator. Because if you have a plus equals for a random access iterator, what you're going to do is you're going to create a constant time operation that just jumps you there. But if you define plus equals for a bidirectional or a forward iterator, you would do exactly what you said, which is you just have a little for loop that just ticks, 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 ticks across. So if someone wants to move 1,000,000 steps in your linked list, that's going to take 1,000,000 cycles of operations, which means that the complexity of moving forward is linear. So there are containers in iterators that do have plus equals defined for non-random access iterators. So when I said before you shouldn't, that was probably a bit rich. It's more like it's like you can, it's just, you need to make sure you're happy to do it, which you would, right, for a linked list, because people do want to jump forward 5 steps. They don't want to create the for loop themselves. Which again, I actually really like standard next as an example for STL algorithms because it actually decouples that whole thing about what container you use. So if someone came along later and was to use a different container, this thing can deal with both containers. One of them's just slower or not.
I think even with the difference type in that case, it doesn't define it there, does it? It just goes
It's saying that it's the type difference type defined by your iterator. So it basically looks up what's in your iterator that's being passed in.
The only other one would be long.
Yeah, I mean, maybe a long. I'm not too sure. I mean, it's always an int. I mean, I've only seen it as an int. That's why it's usually... There's a bunch of stuff. The thing with iterators, you have to accept to some extent that there's some silly stuff there, if that makes sense. Because when nearly everything's a difference type, there's a part of your brain that's surely this must be different. Otherwise, what the hell are we writing this for? Computers should be able to figure this out by now. And I'm not saying there's never a difference, but that feeling is pretty common with some of these boilerplatey things because you're surely this should be deterministic, but it's not. There's a little bit of boilerplating going on. So don't sometimes it's easy to overthink this stuff and be like, oof, feel like I'm missing something. Can you inherit from... Can you inherit from int? I have no idea. That's a wild idea.
I imagine that's what difference type is useful because you could have a subset of int difference type. That's you only allow certain numbers to be inside a difference type. That's why you have a type.
The memory is like that.
Yeah. And you have every size and steps.
Maybe.
Size t, some sort of type size t.
Yeah, but I think, and this is where I tripped myself up 5 minutes ago with it, you're not really talking about the size of the memory. The difference type is purely it's like a step counter. That's why I think it's always int, because it's how many steps, how many hops are you doing? 1, 2, 5, 10? It's always going to be a number. It's not a char, it's not a size t, because a size t is a type defining, I mean, it could be size t. Size t. Yeah, exactly. I mean, yeah, it probably should be an unsigned int or something like that, or size t would probably be fine. But yeah, whatever it is, it's like a number. Has nothing really to do with the size of the type. I don't know much about if there's any inheritance with primitive types, but I don't even know. Wonder if it tells us what size t is. Unsigned integer type of the result of size of, a line of, and offset of, depending on the data model. It's basically saying it's the type of size of, okay. Yeah, I mean, Again, size t will be of size int, or on some weird systems like a slightly bigger number or a slightly smaller number, like a short maybe in some scenarios. I'm not too sure. Yeah.
So we're not actually handling the jumps. Where is that at? Is that the compiler?
Handling the jumps.
Yeah, because you said +5. You're never going to have to implement them.
Well, it depends. Like the jumps is actually in this case happening like here. Though.
Not just moving the memory element along.
Yeah, no, that's it. Like, well, I'm about to show you another example where it's like, yeah, let's look at another example. So the slides for this, it's like the least exciting slides in the course, and we've kind of looked at the slides, and you've probably been like, conceptually vaguely grasp everything, mostly still not feeling great though. You'll kind of cover this. You'll kind of cover this in your shoots next week. I accidentally like pocket called. If anyone was paying really close attention, I kind of like went a bit space cadetty like 20 minutes ago for like 20 seconds. I was hearing this voice talking to me, and I was like, I think it was my headphones, and I pulled out my phone, and it was just like my phone was like on a call for like 10 minutes, and I could hear someone's voice being like, hello, hello. So I don't even want to think about what that was.
Is it a random number?
I hope so. I'm not going to look. It's easier that way. Just ignorance is bliss. What am I looking at? Oh, your exercise repos. Yes. So I'm not going to go through it in detail because your tutor should go through it next week. But one of the best exercises in the course to spend time on, a super big hint for assignment 2, is 5.6, I think. Ropeful. What a funny name. In your class next week, if your tutor looks at this, and hopefully they do, they will code this up with you. And what Ropeful is basically implementing a container and an iterator. I don't want to spend the time kind of clicking through it now just because you're going to go through it in the tute, but I do want to talk to the solution a bit because it'll kind of make some of the abstract slides I was showing you a bit more concrete. But just to understand a rope, as I'm pretty sure, the idea of a rope container is a really interesting one. It works really well to understand containers and iterators because how it works is that, maybe I'll start here. You basically create a standard vector of standard vectors of standard strings like this. And I might butcher this slightly, but it's a 2D array of strings. And this makes sense because if you think about it, you might have a, I think it's a 2D array, or is it a 1D array? Let me check. Gonna ABC fact check myself here. What do we got? Where's the type? Yeah, as I said, don't listen to me. I got confused because there's a 2D array of chars, which is a 1D array of strings, if that makes sense. So it's basically like a list of words, right? Like Hayden really sucks. Like that. And the idea of a ropeful class and a ropeful iterator is that, okay, it's a container. You're going to make a class, and that class contains a vector of strings. Sure. Getters and setters, pretty manageable. However, you make an iterator for that class where when someone iterates through it, they're iterating through chars, right? And those chars are like this: HAYDENREALLYSU, like this. So for the person who's interacting with your container, they don't see that it's like an array of strings or whatever. They just get like a stream of characters. So to someone using it, it's just like a nice flat list. And it's a great way to understand iterators because it allows you to be like, oh, okay, I get it now. We have a container, and the iterator is just like a nice simplified abstraction of that container that someone can just move through and look through and jump through, etc. And it's a great tutorial exercise for assignment 2, like probably more useful than the slides, because if we look at it for a second, maybe let me just copy and paste this in. There's a lot of stuff here that you probably should define in like a CPP file, not in a .h. But this is the container. It's straight from the tutorial exercises. It's called rope, and it has an iterator defined inside of it. But let's just like pretend that's not there for a second. Yeah, and I'll get rid of this too. Oh, it's mostly, and I'll get rid of the dot begins and dot ends. Oh, okay, it does nothing besides iterating apparently. But my point is, you could add some getters and setters if you really wanted to. But right now, it will simply take in a vector of strings, and it will store it as a vector of strings. Standard move is something we don't talk about till next week, but standard move is a C++ abstraction that allows you to do kind of the equivalent of copying, but instead of having to recreate the data, it actually just like shifts it to another spot. It's really useful for large data types when you want to like not use a reference, you actually want to just take ownership of it. It's a little bit weird. It's never really meshed well with me personally, but not really relevant right now. I could do that and it would be the exact same result. It's just a rope that's being passed in. So someone initializes this class, and then what we have is we have a bunch of begins and ends, which we'll kind of come back to. But most importantly, we have our iterator class. And our iterator class is a bidirectional iterator. We could make it a random access one if we tried really hard. There's no reason we couldn't, right? Like, we know the vectors. We could probably figure out the maths to like jump around randomly. But this particular example is not random access. The value types are char. The reference is defined as a reference to the value type. The pointer is void. Can't remember why that is. Oh yeah, pointer difference t. Also a little weird. We'll come back to that. And what we're saying here is that this class, because remember, iterator itself is a class. Let's look for the member fields. There aren't many here. It's just these ones. These are the three pieces of data stored inside the iterator. So when you create an iterator, rope.begin, rope.end, you are creating those three data types. And you think, well, what are those data types? Well, if we have a look up here, outer t and inner t, they themselves are types. And what's interesting about this is we're actually using the iterator type of the underlying structures. So what we're doing here is we are storing three iterators inside our iterator, where the first two are just iterators to our underlying vector list, our vector of strings. And this one here is our inner iterator pointing to a particular string element. A little bit heady, but again, sit on that for a sec. This piece of code, normally we'll spend like 40 minutes in a tute on this and kind of type it all out. But bear with me. When we create our, I should really call this like rope iterator, just so no one's confused, right? Sorry? Oh, you want me to control F the word iter in this big giant mess of code? be pretty fun. Yeah, I probably will screw it up. There's probably a few others. Yeah, there's a few things. So the concept of this is like what we're doing when we initialize it is we identify the very last end of the rope, and we do that by trying to think of a quick way to explain this. I'm not used to explaining this briefly. Let's imagine for a second we just have our rope up here. Hayden really sucks, like that. And how this particular implementation works, which is fairly smart, is, well, you know that this is a vector, right? So we got a few things going on here. If we were to say, get me the end of the vector, we're going to get this point here, right? Because there's a vector with three things in it. So if I did vector.end, I would get one past the end of the vector. Okay, so well, we store that here. That's what this is. We say the end of the rope, but it's literally just the end of the vector overall. Then what we do is we store the outer element, and don't worry about this implementation code here, just focus on this down here. This is where we figure out what particular string are we pointing to right now. Is it this one? Is it this one? Or is it this one? You know, because we need to know where in the rope we are. Like if we're moving through it, at any given time, we're in one of the strings. So that's what that outer one is. And then the inner one is, if the outer one is pointing to this here, which particular character are we currently pointing to within that string? You know? So if you kind of forget about this last one for a second, that's just there to figure out where the end is. Don't really need that. The outer and inner makes sense, because if you were to construct an iterator that was like had to figure out where you are at any point, all you really need to know is like, which vector am I in? Okay, and which which word am I in? So we store those two things to make it work. Then what's interesting is if we start thinking about how some of the operators are implemented, it actually gets pretty easy. So if we think about a double equals operator, well, broadly all we need to do here is check if I have two iterators, are their outer and inners the same, right? Forget about the last stuff, we'll come back to that. Like if I have two iterators, are they both pointing to the same string, and are they both pointing to the same character in that string? If the answer is yes, then I know they're equal. If I want to dereference my iterator and get a particular character, well, I just dereference my inner iterator, because my inner iterator is always pointing to a particular character, right, in my string. Well, when I want to go, and then we have minus, minus, and plus, plus of the post increment are just implemented in terms of the pre-increment, right? So these don't mean anything. They're just saying use the pre-increment to figure this out, because this here is just them using pre-increment to do post-increment. So then it's like, okay, well the plus plus and the minus minus are where things get a little funny. And you think about it, you're like, yeah, that's true, because like if I'm trying to move through my vectors of strings, well, it makes sense just moving a character, but what if I get to the end of my string, right? And then I've got to jump to the next string in my vector list. So you look at what it does. Well, the first thing it does is increments inner, right? Which means if I was pointing to E, I'm now pointing to A. So it just increments which character it's pointing to in the string. And then what we do is we say, while outer is not equal to last and inner is equal to outer end, we go to the next string. So this while loop, again, you could sit down and really make sense of this. I don't expect me to just say it and you'd be like, oh, I'm following that exactly. But this while loop will only be true, the condition will only be true if I'm at the end of the string. So we'd never actually enter this while loop in this case because we're just at the A. But if you imagine that we started at, say, if we started at the Y, let's imagine this, and then someone did plus plus on an iterator, and we had to move to one past the Y now, so we're at the end of our string.end, then outer iterator would be, sorry, if it's not equal to last, and I'll reason with that in a sec, we would actually have to go into that, and then we would have to increment the outer iterator, as in we'd have to go from one string to another, and then we'd have to set the inner to be like the begin of the string, right? Because we're dealing with like our vector 1, 2, 3, and then each string has a bunch of characters. So we're saying, all right, well, we've hit the end of our string, so we've got to go down one row in the vector, great, and then that's our new outer iterator, and then our inner iterator is just, as far as your eyes see it, me, I guess, it's just the beginning of that string. So that's how we set it. And then the operator minus minus is just the opposite. So these are two quite heady functions because they are dealing with the whole moving left and right. And to a user, someone incrementing using an STL algorithm, it's pretty straightforward. It's just like, they're just like, oh, I'm just moving left 3 spaces. Whereas you, the person defining the iterator for the container, you know that you've got to like jump around a bunch. So all of that complexity is abstracted away to you. And yeah, there's some like, this is like setting up an iterator and things. Again, there'll be tutorial stuff on it. We'll probably share a recording of that question too in the notice next week. So I don't want people to be like, oh, I still don't get it, because the point of that was not really to make sense of this fairly long-winded question. It was to show you what it concretely might look like, you know. And there's a few other things to unpack. But if we just go further down a bit, because that was all the iterator definitions, what I also need to show you here is the sorry, I just need to log in so I can see the comments. There's a few comments. Okay. Is like when I go define the dot begins and the dot ends, well, let's have a look at how they're defined, because I simply, what is this? Yep. So what this function's saying is it returns an iterator, .begin, as you'd expect. And when I return this, it's basically passing those two things into the iterator's constructor, which is here. And you can see that the iterator's constructor takes in the first and the last. And it starts to make sense what's happening, because you're giving it the, because I glossed over this last point here, but the last is literally the end of the rope, because if you have a vector of strings, what your iterator needs is the start of the vector and the end of the vector. If you don't give it the end of the vector, it will never know where the end of the vector is. Because notice that your iterator itself doesn't actually ever get the vector object. It only really gets the, well, it's a bit dramatic. It's kind of got, it never gets the vector object. It only gets the vector iterators. So when you call it, you give it the start of the vector and you give it the end of the vector. Those two things are passed in here. You store the end of the vector, right? You store the start of the vector. And then this one, you store the character you're looking for, you know, in that particular vector you're at. See, your mind's just whirring. So focused.
Just speed it up anyway. Why not just have like a matrix definition where you just give each character just a number identifier?
Does this speed it up much? I mean, look, it's a bit of a, like a lot of uni examples, it's a little bit of a silly example to some extent. Like I couldn't tell you right now, or I'd be like, oh, I'd use this exact rope solution to solve this particular problem. But there would be problems like this where you have a particular type of data structure or collection of STL containers, and you want people to be able to easily use it, particularly if it's like a widespread library. But there could be another solution as well. The main point is that the main point of this exercise really is that you're creating an iterator that expresses the structure of the data in a different way to how it's being stored. And that entails some mangling, you know. Mangling in this case being like you have to correlate what a linear list back and forth looks like in terms of something that's more 2D. So the point is, last is the end of the vector, out is the start of the vector, in is the current character you're at. So when you call .begin and .end, you just give it the beginning of the vector, end of the vector, and it goes and figures out for us that the inner element's just the beginning of that particular vector. If you step through this code, it makes a lot of sense. I look at the end, it's the same thing. I just give it rope.end, rope.end. That's how I've defined it. The const ones are the same because we need const versions of it. The C begin, C end ones are the same. We can just leverage begin and end in those cases. That's totally fine, because even though these are non-const, they get kind of put as const. Then we're using the reverse iterator and the const reverse iterators here. And it's like, oh, wow, we're done, you know? So the actual container definitions here were pretty straightforward. But it is, you can't really do these two things in a vacuum, because to define the container's definitions of begin and end and stuff, you need to know how the iterator works. And the iterator, you know, that same person does both of these. It's not really like a divide and conquer thing. Like you just kind of come along and be like, oh, I'll just like write some iterators. Because they do rely on each other's knowledge. And this wouldn't be the only way you could do this either, right? There'd probably be other ways here. This way is particularly clean in that it doesn't, you know, it uses abstractions that already exist. Because some of you could be like, oh, I know, I'll just get an iterator to go and like loop through the vectors and I'll just make an array of elements, you know? And then I'll just like move through that array easily. But what's the problem with that? The problem with that is that, well, now your structure is basically unable to ever be changed, because the second your iterator is invalidated, you have to go and do it again. But even that's okay, because that's kind of true for a lot of iterators. But the problem with that approach, what if the rope had like 1,000,000 words in it of like 100 characters each? Now your iterator only works because you're literally copying the data somewhere, you know? So the nice thing about this one is if you pay attention, this iterator has a memory footprint irrespective of the size of the container. That's just basically 3 pointers. You know, so you could trivially do this, and I would encourage you to, if you like. That's the thing. Don't be scared to write some dumb crap sometimes just to get going. Like if you made an iterator that all it did was just copy data into an array, and then you got the code compiling like that, I'd be like, great job, you're halfway there. You know, it works. It's just wrong. You know, so go and make it better now. Any way you can build confidence is good. Like even I look at this stuff and I'm like, ugh, this find if not, blah. Because this here, from what I can tell, looks like it is mostly designed to be used. Yeah, it's mostly edge cases. Like a lot of this last stuff and things, you could go and implement a lot of this really trivially. Like I could get rid of so much of this if I wanted to. LHS.inner equals RHS.inner. And I think that's one thing I want to kind of leave you with this example is that yes, so much of this example is just dealing with a couple of edge cases. And if you were to try and go and implement this, and I maybe encourage you to before you look at the solution in too much detail, you would find that it would work for 90% of cases with half the code. So my main point here is like, don't think that stuff like this is all super scary. It's like someone trying to deal with the fact, because you get into some weird situations with like empty strings too. That's why there's a while loop. I don't know if anyone was paying attention to that, but like, you can't just think, oh, when I get to the end of a string, I'll just jump to the next string. Because you know what? Someone might be a real poo-poo and give you a string like that, right? And if someone was to do this, the iterator still needs to have that exact same output. Because the iterator can't return nothing. These are empty strings. So then like, if you get into this case and you're currently at n and someone increments it, you need to somehow jump down to this r. You know, and that's an edge case. That's what I mean about like this while loop here looks really scary, and you could probably implement that in much less lines if you weren't worried about empty strings. So don't be too scared of the example, because half the code is just dealing with some BS.
So in that case, in the empty string, what would it see? It would be like it's a last element, it's automatically a last, the next one automatically a last, and so forth, keep going. So it's going to.
Can you say that again? Sorry.
So is it just automatically going to see that the empty string is just at a last?
Yeah, exactly. Because when it gets to the next one, the begin of that string is the end. Because when you have an empty container, the dot begin is the dot end. And that's what this like, yeah, outer, something like that, right? It'd be one of them here.
So just cascading down.
Yeah, just kind of, yeah, cascades, exactly, until it finds like the next point. This is a messy piece of code. Like if I was just sitting down by myself, this would be like, and I'd never seen it before, this would be like some hours of messing about. But the point is, like, you have the lecture slide examples, you have stuff like this. The assignment is very similar. This is, the point of this was not to help you understand this example fully. It's like, you've got enough code now that you could feel like you can piece together stuff and play around with it, you know, for the assignment. And that was the main point. Yeah, someone asked about the friends. They said there's a lot of friends here. Like, why is the iterator friends with the rope? Well, let me see. So the rope, how are we using the rope here? I don't.
Isn't the friend just overloading it? Friend class.
Yeah. Oh, I guess that means that the rope has access to the iterator. I'm not too sure. I couldn't tell you off the top of my head. Let me again rain check you on that one. That's a good forum question. Everything else here makes pretty well sense. This is what I mean. Stuff like this, you would copy and paste that. You know, that's not like code you sit down and be like, I've got it, and then you write that out. You just copy and paste that.
Would the friend there be able to, friend class rope means it'll be able to access everything in the class rope, anything statically defined. Any private members.
Where I'm confused, and I don't deal with friend classes a lot, is I feel like this is saying that the class rope is a friend, and therefore the class rope can access things inside this. But where that puzzles me is that this is a class within rope. So I don't. There's probably a very reasonable answer for an average person, but I can't see why that's necessary if.
Is it defined as part of it at the top?
Well, it's within the scope of it, right? It's like everything inside the class is, like the class can act, like rope can access this because it's defined within the class, you know? That's just like kind of class rules.
But can the iterator access?
I don't think that's what it's saying, but even then the iterator I don't think does, because if you actually look at what the iterator is doing, it only ever the iterator only deals with the begin and the end of the rope classes, the begin and the end iterator of the rope classes object. It only ever deals with rope underscore begin and end. It never actually does a lot with the rope object itself. So, not sure.
I think the question is, can any member from row access anything inside item?
Can it access anything inside the iterator?
Yeah.
Yeah.
Iter class. So can a member function of row access anything inside item, like any member of item?
I think it should be able to. I could be wrong. Like, I'll be honest, I don't know the answer. I can't see why it wouldn't, because it's...
It should be able to, then there's no need of declaring friend class.
That's what I think, but there are people smarter than me that glanced over this code when we wrote it 5 years ago, and they left it there. So I'm sure they left it there for a good reason that isn't apparent to me right now. Maybe. Or maybe it's just dumb luck. I'm not sure. Someone will figure it out in the next week, and I'll... Yeah. First person to figure it out, I'll pay ID you $1. That's my new thing I've been telling students, because it's easy. So if you want $1 to your bank account, figure it out and post on the forum. You're not motivated for $1, are you? No, didn't think so. Any other questions about this? Just because I want to move on to the assignment 2 stuff.
About that for the different T.
Oh, yes.
Yeah. Is it because we're dealing with class, so we need a larger data type for that?
Larger spacing between the members?
I remember this now as we look through it. I'm not 100% sure. My memory of this is that it's basic. It's kind of the iterator abstraction for an int. I don't think it's anything specifically different from what we're looking at previously. But it's a little weird. I'm not too sure. Point of difference has always, difference type, sorry, has always eluded me a little bit. Just on account of the fact that, you know, it's somewhat so unnecessary a lot of the time. But just to be clear, it's one of those things where, you know, from our perspective in the course, because what's hard about assignment 2 is like, there's some things that I can't be like, use that exact one in assignment 2, because then like no one ever thinks about it. So there's some benefit for me kind of being like, oh, you should probably figure it out. But it's like, if it works with this stuff, you know, with these iterator traits. Like, I wouldn't be too stressed about something like that as long as it compiles like in point of different, like size t. If someone did size t and had a good rationale for it, I don't think we'd ever take marks off. We'd just be like, well, it's not that, you know, just a quick note. Yeah, leave that one with me too. I want to go read up on that a bit more. Cool. Just to, yeah, that's it.